Hi, thanks for attending my talk on clinical user-centered explainable AI for medical image analysis. As AI becomes pervasive in the society, we're concerned about its safety, accountability, and trustworthiness. This problem is more prominent when we are using AI for critical decision support, as shown in those healthcare scenarios. When doctors are using AI, they usually require AI to back up its decision with some rationale. This is an explainable AI problem that aims to explain AI decisions in human understandable ways. In medical image analysis tasks where AI provides a prediction given a medical image, providing explanation can give doctors the informed decision support so that doctors can incorporate the explanation as another layer of clinical evidence into their decision workflow. However, when we are considering the problem of explaining decisions to doctors, we'll find that many explanation techniques are not suitable because those techniques are designed for technical users for their model debugging purposes. And interpreting those explanations would require doctors have technical knowledge in machine learning or AI so that they can understand what neurons or latent representation means. Therefore, the goal of this survey is to identify and review end-user-centered explainable techniques. So to see what our end-user-centered XAI means, we can look at the physician's image interpretation process and dissect as two processes. The first is extracting of human interpretable features, and then we reason based on the features. We can see that the feature extraction is the cornerstone because the reasoning is built upon it. And furthermore, for the features, it can be represented as either image region or text description or both. Therefore, we can identify the end-user-centered XAI techniques if it represents their explanation in either the image or text format, as shown here. And specifically for the image format, it can be further divided into two categories of showing only the image regions or similar patches of the image regions. So now we have identified the end-user-centered XAI techniques and their categories. There are some high-level technical ideas behind those techniques, which I summarize as decomposition, visualization, and alignment. They respectively translate the latent and interpretable representations into low-level, mid-level, and high-level human understandable terms. And for each of the category, it has different approaches to achieve these goals. And I will review their representative or landmark works in both in those categories. And we can actually see there between the method and the form, there's a good correspondence. For example, the decomposition and visualization method, they are represented by the explanation form using image regions. And for the clustering method, they're represented as similar image patches. And for the alignment method, they're represented as the form of concept or concept and image combined. And we can see there's the high-level philosophical idea behind those methods. They all use reductionism. That is, we try to describe a complex system, such as a neural network, using some simpler and fundamental parts. So this is the outline of my review. I will review each of the methods and then talk about evaluation, the ethics, and the future directions. Let's first look at the decomposition. This line of method try to decompose the contribution to the prediction into this low-level interpretable features. And those features can be shown as the importance of image pixels or superpixels, as shown in this feature attribution map, also called saliency map or heat map. So given a very complex nonlinear models, if we want to explain its local behavior for this local input, we can, the very intuitive way is we can use Taylor polynomial to approximate this complex function. For example, this tangent line is the first order Taylor derivative, and its gradient can well decompose the total contribution of the decision into each of the input features. As shown in this gradient saliency map. So this method is called the vanilla gradient method. It's very easy to compute. You just do one pass of backward back propagation. Despite its computational efficiency, the gradient has a drawback that you can see that its feature tends to show very low level detailed features, which to our human eyes is noisy. So to overcome this problem, we can actually aggregate the local information by the neighborhood sampling. So for example, we can add some Gaussian noise to the input image so that we can sample around its neighborhood and get an average gradient signal. This method is called smooth grade that aims to remove noise by adding noise. And you can see the resulting heat map show is much cleaner than those original gradient map. Another way that also follows the neighborhood sampling is called LIME, local interpretable model organistic explanations. So to explain the red cross, it also sample around its neighborhood, record the input, the model's output, and their relative similarities. And they use this as the data set to construct a local interpreted model. Here they use the sparse linear model and use this local linear model as a proxy for this original complex model. So this is a line method. So now we have two methods of linearity and neighborhood to tackle the decomposition problem. Next, we look at another method called marginal contribution. So the margin contribution want to fairly attribute the total contribution of the prediction to each of the features. And ideally, we want this contribution to be fair and fulfill those properties. The parts sum to the whole, and the features row is linearly active. And if their features row are the same to the model, their contribution should also be the same. And similarly, if the feature is ignored by the model, its contribution is zero. We can see that the Shapley value is the only solution that fulfills those properties that fairly contribute the total prediction to each of the feature. And it's calculated using this formula. Basically, this is the weighted, the average marginal contribution of the feature across all feature combinations. So we can see how we calculate the Shapley value manually using a very simple example. So in this example, we have these three features, and they have the total model performance of 15. So we want to see what's the importance of feature A. We can calculate the feature importance using the Shapley value. So this is a Shapley value calculation. The first is to get all combinations of the feature subsets S. So we list different feature subset S that excluding the given feature A. And then we calculate the model performance difference with the feature A and without the feature A in each of the S, and get this difference score, performance difference in their model with respect to the model performance matrix. And then for each of the combination, we weight by their relative probabilities of their occurrence, the combinations probabilities in this combinatorial sets. And then we get this Shapley value. You can see that to calculate the Shapley value, we need to do the exponential permutation for this different set of feature combination. So there are some methods to the sampling that reduce the computational complexity from the exponential to polynomial time. So now we have seen the different approaches for the decomposition category. So next we move to the visualization categories that try to visualize the latent representation as middle level features. We first look at how we can visualize the feature map. So the feature map is just the internal layers in a CNN, which has a 3D shape. So to summarize the information, we can regard each of the 2D shape as a spatial correspondence to this input image. So we aggregate those different feature map together using their relative weights from the decision process. And this is a class activation map that highlights the important regions for the model prediction. Another way of visualization using feature map is utilize the attention mechanism. So here in this work by Yan et al., they worked on the melanoma detection problem, and in this vanilla VGG model, they add the 2 attention modules. So for each of the attention module, it has a guidance feature that guides the original feature map and to aggregate them together to get this attention map. So we can use attention map to visualize what the network is paying attention. So that's 2 ways to visualize the feature map. So now let's look at the another approach for visualization, that is clustering. As I said, the internal representation is like 3-dimensional, and the clustering is to try to cluster a semantic similar latent representations. A landmark work on clustering the feature maps is called the prototype map. It modifies a CNN model by adding a prototype layer. The prototype layer consists of a group of prototype vectors, each representing the prototypical features in class. It's like a clustering center, and each location of the image patch is compared with the prototype vector to get the similarity. The prototype layer are joined to learn during the training, and the loss function regularizes the images to have the similar some latent patches to be close to at least one prototype of its own class, and to stay away from the prototype if it's not in its own class. The decision is reached by aggregating the similarity score with its learned weight. At inference time, the similar image patches are grouped together to represent the similar feature so that users can compare the localized feature with a series of prototypes. So this is a visualization approach to visualize the feature map and to clustering the feature map. Now let's look at the third category, to alignment. The alignment is to explicitly find or align the latent representation into the high-level human concepts. We look at the concept-based explanation. A landmark work is called the CAV, the concept activation vector. This is the explanation from the CAB method, that to explain the decision on the dumbbell, it lists the 3 most important concepts for the model prediction. And let's see how it did. So given a already trained CNN model, it used a linear probe to probe into the latent representation. So the linear probe is constructed using similar idea from the linear decomposition. Like we see in the LAM method, we train a linear interpretable model to try to separate the concept. So here is the linear vector for the concept straps. and it gives some positive example and negative example. And if the vector, if this decision boundary can well classify these two examples, then we can use the vector that is perpendicular to this decision boundary as the concept vector. And we can calculate the relative difference from the decision to the concept vector as a concept sensitivity as a quantified measure of this concept importance. So this is the CAP method. Another method is called concept whitening. So this idea is to, instead of probe into the latent representation for already trained model, this method is construct during training. So this is like interpretable, inherently interpretable approach. So to do so, it replaces the normal batch normalization layer in the CNN with the concept whitening layer. So what the concept whitening layer do is it also do the normalization approaches as we see in this, it do the mean centered. And after that, it also do the whitening to decorrelate the different vectors and do another step of rotation so that they can align each directions represented in each of the neurons with the human high-level concept. So in this way, during training, the model latent representation is more aligned with the axis of the human concept axis. So this we see two methods in the concept region, and then lastly we look at the intermediate step. So those approaches is try to directly, explicitly train the neural network so that the intermediate step is showing the human understandable concept. Actually here, for example, in this model called concept bottleneck, it's utilized the two-step approaches. So first, we use a normal CNN and we insert a concept layer so that the CNN can predict the concept label as an intermediate step. And then based on the concept label, it then predicts the final task label. So during training, we had two loss functions. One is task prediction, the other is the concept prediction. And another way, so instead of using the concept label as the intermediate step, another way is to use the semantic segmentation maps as an intermediate step. So we, to classify this OCT scan, we can first do some segmentation training to train a segmentation model that can output the semantic segmentation for this lesion map. And then we make prediction based on this tissue segmentation maps. So in this way, if doctor want to trace back what's why the model make prediction, they can look into this segmentation map. And this segmentation map can both show the lesion and their locations. So now we have seen different methods that try to translate the latent representation into this low level, middle level, and high level human interpretable features. Next, we briefly look at the evaluation, ethics, and future directions. So for the evaluation of XAM method, we have two principles. The first principle is that we want to the AI explanation to follow the same assumptions in human explanation. So the first human explanation is that so the evaluation of XAM method follow two basic principles. The first principle is that the evaluation is to see how the AI explanation follows the assumptions in human-human explanations. The first human-human explanation assumption is that when we are using explanation, we assume that explanations faithfully reflect the model decision process. So we want the same for as a evaluation for the AI explanation. So this in the literature is called faithfulness or truthfulness evaluation. So that is to see how truthfully the explanation can reflect the model decision process. To do so, we can do the gradually remove or add the feature and see how the model performance drop. If the model performance drop quickly, that means those identified features are important for the model prediction. And the other method is to conduct some synthetic data set. With this data set, we know the ground truth feature importance. And if the model learned well, they capture the ground truth feature importance. And then we measure how the explanation align with those ground truth important features as a measurement of the faithfulness. And the other assumption in human-human explanation is that when we use explanations, we expect that the right explanation corresponding to the right decision, and the wrong decision has unreasonable explanation, and we require the same for AI explanation. This is called the verifiability matrix that measures the correlation strength between the model decision quality and the explanation plausibility or reasonableness. And another principle for evaluation is that we want the explanation to be useful, so that the explanation can fulfill the user utilities when using explanations, such as to verify decisions, how to solve decision agreement when doctor and AI disagree, or help user to make new knowledge discoveries, or help users learning or communication. So we can conduct human subject experiments to see how well those explanations in their performance in those users' utilities. And the other utility is by using the explanation, user want to improve their task performance so that the task performance is better than either the human or AI alone. This is called the human AI team task performance. And we can also conduct the human subject experiments to directly measure the team performance. So this is the evaluation method. And let's look at the ethics and social implications. So currently, the technical solutions are narrowly focused, as I mentioned before, focused on the technical users' solutions rather than the end users' purposes. So that causes a problem, as I mentioned in the beginning, that doctors they may not use the existing techniques. And that's why we say that the social right to explanation is important for the end users, because we know that the model may be problematic, probabilistic, and can make errors, and sometimes the evaluation matrix, the data input or output predictions may not well align with users' end goals. That's misalignment between the algorithmic objective and social objective. And because of this misalignment, it's important to provide user with some form of explanations so that users have the right to challenge or question the decisions made by the automatic system. But while we are providing explanations, we need to also be aware that explanations sometimes can be used as a form of manipulation. There are many studies that shows that simply showing a plausible explanation can lead to the over-reliance or over-trust problem for the users. So we need to responsibly use explanations in those critical tasks. So with this, we have some future directions on end-user-centered AI. At a high level, we need to design those XAI techniques to align with human decision-making patterns and follow human explanation assumptions, and can fulfill users' utilities using those explanations. And there are some fine-grained, detailed questions or for future works. So that's all for my presentation. Thank you very much.